All right, hey there, guys. My name is Wilfrid. I'm a senior math tutor, and today I'll be covering 11 questions based on algebra. And a little backstory upon myself: I graduated from a master with a major in biochemistry and a minor in mathematics. And if you have any other issues or problems with your questions, please submit them through OneClass, and we'll get to them as soon as possible. Other than that, let's begin. Okay, so the first question reads, what is the square root of 50 in the simplified radical form? So before we even begin to tackle this question, there's a few properties of square roots, the square root function that we can use to help find us the simplified radical form. Okay, so the first property that we're going to use is this. So if we have the square root of, let's say, a times b, we can write this as the product of the square root of a times the square root of b. Okay, so that's what we're going to use to help us find the simplified radical form. So the technique that I like to use and I like to utilize for this is to find the prime factorization of 50. And what I mean by the prime factorization is to break up 50 into prime factors. And prime factors are basically factors that are prime numbers, and prime numbers are basically numbers that can only be divided by 1 and itself. Okay? So let's look at 50 and let's try to find the factors of 50, okay? So 50 has a lot of different factors. We have 2 and 25, for example, right? 2 times 25 equals 50. We can have 5 and 10, right? So we're going to use either one is fine. So we're going to use 2 and 25, right? So we see here that 2 is one of the prime factors of 50 because it's a prime number, but 25 is not. So we can further break this down. So you can further break down 25 as 5 times 5, right? So now we see here that the prime factorization of 50 is going to be 2 times 5 times 5. All right. If we were to do the other pairing, for example, 5 times 10, we see that 5 is a prime factor, but 10 is not. So we can further break down 10 into its prime factors, and it's going to be 2 times 5. And we can see here that the prime factorization is always going to be the same for any number. So our prime factorization here is 2 times 5 times 5. So how does that help us with the square root of 50? So first of all, the square root of 50 can be written as, sorry, just give me a moment as I adjust my writing pad. So the square root of 50 can be written as the square root of its prime factorization. Okay, sorry. Which is 2 times 5 times 5, right? So we already know that 2 times 5 times 5 is equal to 50, right? We can alternatively write 2 times 5 times 5 as 2 times 5 squared. Okay, so we just took these two 5's together, and 5 times 5 is also equal to 5 squared. Finally, we're going to apply our property of the square roots, and we're going to break up this square root bracket. So we're going to have the square root of 5 squared times the square root of 2. So we see here that the square root of a squared number is just the number itself, and that is going to equal this. And the square root of 2 is not a perfect square, so we're just going to leave it as the square root of 2. And this is the simplified radical form of root of 50. And we see here that we got there by finding the prime factorization of 50 and then breaking it down so that it's in its most simplified form. We see here that we're square rooting a prime number and it doesn't have a perfect square at all. We can approximate it by using a calculator, but we're going to leave it as such. So this is what we call the simplified radical form. It consists of a whole number times times a square root of a number that is not a perfect square. So other than that, this answer is correct, and we can move on. All right. So the next question reads: evaluate the log of 2, log base 2 of 16. Sorry, just give me a second. I'm just going to reduce some noise. I can hear it. Okay, so the next question reads, evaluate the log base of 2 of 16, okay? So I'm going to write another property of the logarithms here to help us find this answer, okay? So the logarithmic function is as such, so it specifies a base that we're using, and it's trying to find the exponent that will give us the 16 from the base, okay? So it's written out as this, and we're looking for a number called y. Okay, so the general form would be log of base b of argument a equals something called x. And this is equivalent to saying um, b to the power of x equals a, right? So this is the same thing. I'm going to write in our arrow as such. So b to the power of x equals a. So it is essentially the inverse function of our power functions, for example. Okay, so the logarithmic function, we input a argument, and it gives us the specific power that will give us the argument with the base to the power of x, basically. Okay, so in this case here, we're trying to look for the power that will make 2 to the power of something equal to 16. So in this case, log of base 2 of 16 equals y is the same thing as this. So 2 to the power of y equals 16. So we're looking for y. We're looking for the exponent, okay? So the way I like to do this with any base is to divide 16 by the base until we get irreducible number. Okay, so let's do this for now. So 16. So if we were to divide it by 2, what would we get? We will get 8. Right? So that's 1. That's 1. Okay, so I'm going to label this 1. If we were to divide 8 by 2, we would get 4. So that's a second 2 that fits within 16. Okay? If I were to divide 4 by 2 again, we'll get another 2. And if we were to divide 2 again by 2, we got 1. So you see here that we have 4 steps until we get to an irreducible number. We can't divide 1 by 2 because it won't give us a whole number again. So in this case, the log of base 16 of base 2 of 16 is equal to 4, because it takes 4 2's, so it takes 2 to the power of 4 to equal to 16. So this is one of the steps that you can do to help calculate logarithmic functions. But after a while, you'll get the hang of it, and you'll be able to do this in your head. But this is good practice, especially with like log base of 10, and so on and so forth. Okay. So this solution is correct. Good work. Okay, let's move on to question number 3. So question number 3 reads, how do you find the domain and range of the natural logarithm? So the natural logarithm is basically like our logarithmic function. And the notation for the natural logarithm is, so it's log of base e, but we write it as ln, okay? So that's what the natural logarithm is, and it's basically the logarithmic function of base e, of the natural number. So the characteristic of the natural logarithmic function, or the ln function, is going to be the same thing as the logarithmic function, okay? So in previous lessons, I've described how to find a domain and range. So the domain is defined as all values that define a function f of x, okay? So all values that are valid and that define f of x. So any values of x, or any values that make f of x undefined, are not part of the domain, okay? And the range is all possible of x, of function f of x. Okay, so the range means that all the values of the domain that map to something else, that those values that are mapped towards are called the range. Okay, so there are many different ways to find a domain and range, and for one, you can use mathematic, I guess, logical reasoning to find a domain, and you can use graphing to find a domain. And in the same way, you can also use the inverse function to find the range, or you can graph it to find the range. There are multiple different ways of finding domain and range. In this case, I feel like the best way of finding the domain and range is to just graph the function itself. Okay, so the junior tutor helped us graph it here. So you see here that this is the behavior of a ln function, and it's similar to the logarithmic function. So we see here that for the domain, it means that it's all values that define f of x, right? So we see here that the domain for this is that all x values that are greater than 0 will define our function. And if you think about this mathematically, this makes sense, right? So we know that ln, I guess, of x is equal to y, right? So this is equivalent to saying e to the power of y equals to x. Okay, so these two functions are related to each other by the inverse, right? So ln function is the inverse of our power function, our exponential function, right? So we see here for our exponential function that no matter what the exponent is, positive or negative, our value of x will always be a positive number. And this is because of the nature of the exponential function. You see here that the base is always going to be positive, and the exponent does not influence the sign of our result, right? So if we were to look at our inverse, that means that that the exponent could be positive or negative here, but our argument will always have to be positive, okay? And if you guys want, you guys can graph your natural logarithmic function to see that this is the case. And let's graph that now, right? So this is our ln function, okay? So if we were to add a different function here and we would do y equals e to the power of x, this is what we get. So you see here that the range of this function is always positive, right? So we see here that no matter what, no matter if we have a negative exponent or a positive exponent, our argument or our result is always going to be positive. So in this way, if we flip it to the inverse, we see here that the domain always has to be positive. The argument of a logarithmic function can never be negative, okay? So we now found our domain. So if I were to go back to our question here, our domain is x such that x belongs to all real numbers and x has to be greater than 0. So that is our domain. Okay, what's our range? So if we were to look at our function again, we see here that our range extends from all the positive numbers to all the negative numbers. So our range is y such that y belongs to all real numbers. Okay, so that's how you visually look at it. All right, you guys can use mathematical logic and your knowledge of functions to try to find a domain. And the last thing is that you can also try to use the inverse function to reason what the domain and range of your original function is. Because the range of your inverse function is going to be the domain of your original function, and the domain of your inverse function is going to be the range of your original function. So if you were to see here as an example, if we're taking into account the range. So the range, the domain of our inverse function, which is our exponential function, is x such that x belongs to all real numbers, right? So we see here that this function continues on and on and on and on, right? It just goes towards infinity, but we reason that all values of x on the real number line are valid and define our function, our inverse function, right? So in that case, the domain of our inverse function is equal to the range of our original function. So in that reasoning, we believe that the range of our logarithmic function is all real numbers, okay? So other than that, the solution is correct and we can move on. Cool. All right, so talking about domain and ranges, we're going to now describe the domain and range of a rational function, okay? So first of all, let's describe what a rational function is. So a rational function is defined as the ratio of two different functions. So we're going to describe h of x as a rational function, and that's equal to the division of f of x by g of x, where f of x and g of x can be any kind of function. Usually in high school mathematics, we usually see f of x and g of x as polynomial functions, but they can be anything, okay? So they're asking us to find and define the domain and range of a rational function, all right? So in the last case, we saw that the domain was restricted to all values of x that are greater to 0. In this case, the domain is restricted to a different set of values, okay? So this has to do with limits, but we have to realize that the denominator function can never be equal to 0, because anything divided by 0 will be undefined, okay? So in this case, the domain, okay, the domain will be x belongs to any real number except for x, except for values of x where g of x is equal to 0. Let me just write g of x equal to 0, okay? So that's the domain, okay? So whatever values of x that make g of x equal to 0 cannot be within our domain, okay? So the range is a little bit more difficult, but we can find the range by finding the inverse function and defining its domain. And by defining its domain, we can find the range, okay? So let's look at an example here. So the junior tutor gave us an example of f of x equals to 1 over x. So this is our typical reciprocal function here. Our function in the numerator is 1 and our denominator is 1 over x. Okay, so if we were to graph this, the junior tutor shows here that our function is not defined at 0. Okay, and this is because when x equals 0, is 1 divided by 0, and that's an undefined value. And you can see here it has to do something with limits. So as you approach the left side from the left side towards 0, you see here that our function tends towards negative infinity. But as you approach from the right side, our function tends towards positive infinity. And because of this disconnect here, we have to say that this part of the function is undefined, and that means that x cannot equal to 0. Okay, so the domain for this is going to be x such that x belongs to all real numbers except x cannot equal to 0. Okay? So let's look at what our range is. So our range in this case, as we look at the function visually, is that on both sides of the functions, they tend towards negative infinity, and on this side they tend towards positive infinity. But as x increases on the negative axis and on the positive axis, it tends towards 0. But however, it will never actually hit 0. So we can say with confidence that the range of this function is all real values except for y equal to 0. Okay? It's going to tend towards 0, but it'll never equal 0. Okay? So you can see here, by visually graphing it, we're able to ascertain the domain and the range. Okay? So other than that, the solution is correct. So in other questions, because this was a very simple one, if you want to find a domain and range of a function, to find a domain, all you really need to do is to set the denominator function, our g of x, to equal to 0, and solve for the values of x that equal to 0. Once you find those values, you know that they are excluded with outside of the domain. Okay, and with the range, you can either graph it, or you can find an inverse function, or you can use mathematical logic to reason out what are the values that are not included in the range. Usually that means that the asymptotes are not included. In this case, in our example, the asymptotes of f of x is 0. So the asymptotes are not included. Okay, so the solution is correct. Good stuff. All right, let's move on to question number 5. All right, so question number 5 reads, how do you graph y equals x squared? All right, so the technique that I like to use is to find some testing points. In this case, we have a parabola here, and once we find the testing points, we can graph out those testing points, and we can extrapolate the behavior of the function from there. Okay, so let's do some testing points here. All right, so why don't we test out? Let's make a table first. Okay, so x and y, and our function here is f of x, or y equals to x squared. Okay, so we're going to plug in some values of x, and we're going to calculate what y is. Okay, so we plug in -3, right? So the square root of -3 is 9. So if we plug in -2, the square root of -2 is 4. If we plug in the square root of -1, it's equals to 1. If we plug in 0, we see here that the square root of 0 is 0. We plug in 1, the square root of 1 is 1, 2, 4, 3, 9. So by doing these testing points, we are now able to plot this on our graph and to graph out these testing points. And by doing so, we can extrapolate the behavior of this function, and we can see what we're looking at, okay? All right, so let's draw out our axis here. All right, let me just zoom out. All right, okay, so I don't know if you guys can see these values, but if you can't, you guys can follow here. All right, so first thing that I'm going to do is going to label your axis. Always label your axes, all right? Let me make use a bigger sized, okay? Okay, so this is pretty, so x and y, all right? X and y axis, okay? So we're going to label out our points now, okay? So we have, I'm going to be pretty big with this, so it's -1, -2, and -3. Okay, this is not to scale, sorry, but 2 and 3, okay? So now we're going to label out our other points. So I'm going to put 9 here. I'll put like 1 like here. And it's not to scale either. I'm sorry about that. 0 is over here. I want to put like 4 in between, like right there. Okay, so now that we have our axis and we labeled out the scale of our axes, we're going now to graph our function here. Okay, so we have 0, 0, right? We have -1 and 1. We have 1 and 1. We have 2 and 4. 2 and 4, and we have -3 and 9, and 3 and 9, okay? So now from here, we're going to graph out our parabola. Sorry. Oh. Okay, let me just try to connect these dots. Okay, cool. So this is equal to y equals x squared. As you see here, that as we had some testing points, we can extrapolate what the next points are going to be. So if we plugged in 4, it's going to be 16. If we plugged in -4, it's going to be 16. So we see that it's a symmetrical function, right? From there, we can also know that we see that our vertex, or our minimum value here, is 0, 0, right? There's no value of y that is less than 0, right? In our testing points here, we tested both sides of the axes. Another important fact is that our y's are always positive, and this is because of the nature of y equals x squared, right? So by doing these testing points, we can come to conclusions about our function. We have a symmetrical function. We have a function that outputs only positive values. We know that the minimum is, or the vertex is 0, 0. We know the behavior of our function, looking at if we increase x, that y also increases. So we have all this different information from using these test points. Okay, so using test points is actually very good as a beginning step towards graphing functions. But once you start to understand the basic functions of the exponential functions, of the logarithmic functions, and how different constants affect them, you don't really need to use these test points anymore. For example, the parabola and the quadratic function is a very good example of this. You'll soon learn that the coefficients of the quadratic function, so our basic quadratic function is actually y equals ax squared plus bx plus c. That these coefficients all mean different things, and they help us to graph out our function without using test points. For example, the coefficient of a helps us to understand how much we scale our parabola by, and the sine of a helps us to understand whether this parabola is concave up or concave down. C, for example, tells us where the y-intercept is, and where the parabola intercepts the y-axis. And by using a combination of these coefficients, we can understand where the vertex is, where the zeros are, and a lot more information. By doing so, we can graph them without using testing points. So I would suggest using testing points if you're a beginner and you're trying to understand how to graph functions. But after a while, you can learn what the different coefficients mean and how they affect the graph, and how they affect how the graph functions, or how the graph behaves. But other than that, the solution is correct, and we can move on. Okay, so let's talk about question number 6. All right. So later on in the lesson, I'll cover what zeros are and what solutions are and what x-intercepts of quadratic functions are. But first, we're going to tackle how do you factor x squared plus 4. Okay, so they're asking us to break x squared plus 4 into its factors, which means that they want us to write, so if we had a parabola, a quadratic function such as ax squared plus bx plus c, for example, its factored form would be probably dx plus e times fx plus g, where d, e, f, and g are coefficients, okay? So that's what they mean by factoring. Another reason why we factor is that we can find the zeros, and the zeros relate to the factors in a way that I'll describe right now. Okay, so to factor this, we cannot use the traditional cross multiplication method to factor it, so we're going to use a quadratic formula instead, and I'll get into the reason why very soon. Okay, so the quadratic formula is described as x, so the values of x equals plus or minus b times the square root of b squared minus 4ac divided by 2a, where b, a, and c are the coefficients of our basic quadratic equation. And these this formula helps us to find the values of x, which are the solutions to ax squared plus bx plus c equals to 0. Okay, so this quadratic formula helps us to find the values of x that make this equation equal to 0. Okay, so we're going to do this with our own example here. So we see here that our function here is x squared plus 4 equal to 0, and we're going to try to find the values of x. Okay, so our coefficient b is not there, so it's 0 plus or minus the square root of b squared, so 0 squared, minus 4 times the coefficient of a is 1, right? 4ac, so c is equal to 4. Okay, divided by 2a, so 2. Okay, so we see here at the end of the day we get the square root of negative 16 divided by 2, plus or minus. Okay, now we ran into a little bit of a problem here because we can't square root negative numbers. Using mathematical logic and understanding our understanding how the square root function works, the square root function cannot produce a result with a negative number. Okay, so we have to use imaginary numbers to circumvent this. Okay, and so another important property is that I, which is the imaginary number, is equal to negative 1. So in this case here, we can see that we can write root of negative 16 as the root of 16 times I, right? So we broke it up into the root of 16 times the root of negative 1, and we know that I is equal to negative 1, our root of negative 1, so we have this now. So now we know what the square root of 16 is a perfect square, so now we have the answer that our solutions to this formula is plus or minus negative 2i. Plus or minus 2i. Okay? So with this in mind, we now have the zeros, and the zeros relate because they relate to factors as such. So now we can break up x squared plus 4 equals 0 into x plus 2i times x minus 2i. Okay? So we can see here that when x equals 2i, this bracket will equal to 0, and anything times 0 is equal to 0. And when x is equal to negative 2i, this bracket here will equal to 0. So this bracket here will equal 0. And 0 times this is equal to 0. So that's how the zeros relate to the factors, okay? So by finding the factor form, we're able to find the zeros that make this equation equal to 0. So that's why we call them zeros. Okay, so these are the factors of x squared plus 4. And we see here that the factors, or the roots, are actually just complex numbers or imaginary numbers. And I'll get into the reason why later on into the lesson, because we're going to cover what a discriminant is and how it gives us information about the solutions to our quadratic equation. Okay, so the solution is correct. Good work. Alright, so the next question is, what is the value of the discriminant given by the equation 2x squared plus 4x minus 2 equals to 0? So last time I covered what the quadratic formula was, right? So x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, so the discriminant is based off this formula. And discriminant, or d, I'll write d for now, is equal to b squared minus 4ac. Okay, so that's what the discriminant is equal to. And the discriminant gives us a lot of useful information about the zeros, or the solutions, of our quadratic equation. Okay, so I'm going to give that information now. So if d is greater than 0, so if the coefficient b squared minus 4ac produces a positive number, then we know that there are 2 zeros. Okay, if d is equal to 0, we know that there is 1 0. And if d is less than 0, we know that there are 2 complex zeros. Okay, so what do I mean by complex zeros? So in our last question, if we were to calculate the discriminant of this, so b squared minus 4ac, so just minus 4ac, we'll get a negative number, right? So negative 4 times 1 times 4 is negative 16, as you see here. And because of that, we figured out that we have 2 complex solutions, or zeros. Okay, so in this question here, by calculating the discriminant, we come to understand how many solutions are there of x that make this equation equal to 0. Are there 2 real solutions? Is there 1 real solution? Are there 2 complex solutions to our equation here? Okay, so to find the discriminant of this example, we're going to calculate our discriminant. Okay, so we have our equation 2x squared plus 4x minus 2 equal to 0. Okay, so we have coefficients a here, b, and c. Okay, so if we use our discriminant equation, we get b squared, or 4 squared, minus 2, or 4ac, or 4 times 2 times negative 2. So 4 times 2 times negative 2, and we get 16 times, minus 8 times negative 2, and we get negative 16 plus 16 minus minus 16, so 16 minus minus 16, and minus minus is a positive, so we get 32. So we see that the discriminant is greater than 0, therefore there are 2 real zeros. Okay. So if we were to factor this quadratic equation, we would find two real, I guess, factors for this equation. Okay. So another way to think about this, all right, is to think about how the quadratic formula works, right? So the quadratic formula is actually really dictated by the square root function here, right? So whatever the result of the square root is going to determine how many zeros we have. And this is because if the square root is positive, this plus or minus value will be maintained within our quadratic formula. So we'll have to calculate negative b plus a positive square root and negative b minus a positive square root. And that's why we have two real solutions, okay? So if this square root was equal to 0, this positive and negative sign would actually be nullified, right? So negative b plus 0 and negative b minus 0 is still negative b. So in this sense, using mathematical logic, we understand that if b squared minus 4ac is equal to 0, we only have one real solution. And finally, if the square root is negative, in our previous example, we have seen that by using the imaginary number, we can circumvent the negative square root, and we would have to do negative b plus a imaginary number and negative b minus an imaginary number, and that will give us two complex roots, okay? So that's another way you can think about using the discriminant by using the quadratic formula and breaking it down and seeing how it differs based on the positive value or the negative value or 0 value of the square roots. Okay? So other than this, this solution is correct. Nice job. All right, let's move on to question number 8. All right, so question number 8 reads, if g of x is the inverse of f of x, what is the value of f of g of 2? Okay, so I'm going to first describe what the law is here, and then we will break it down and we'll try to understand how this law works. Okay, so if g of x is the equals to the f of inverse, so this is the notation of the inverse function. So we have a f to the power of negative 1 of x, right? So if g of x equals f of inverse of x, then the f of inverse of f of x is going to equal x. Okay, and why is this so? All right, so if we have a compositional function of a inverse function within a function or a function within an inverse function, we're going to get x, and this is y, okay? All right, so if I were to draw out a diagram here, so this is how functions usually work, okay? So we have a group of values and we call this our domain. Okay, and we have a function, let's say f, that brings our values in this circle to a new set of values called our range. Okay, so the function is kind of like a bridge that connects or maps one value in our domain to another value in our range. Okay, so the f of inverse takes values from our range and maps it back to a value in our domain, and it's going to be that same value. Okay, so the f of inverse just reverses whatever the function does. So you think about it like two locations, right? So you have home and you have work. So this is the transportation from home to work, and this is transportation from work to home, right? So let's say, for example, that we have a value a that's valid within our domain. It defines our function, okay? So that means a is mapped by f to be equal to, let's say, a value b. in our range. Okay, so if our function maps a to b, then our inverse function is going to take b and map it back to a, right? So how do I describe this? So maybe I should do something more like, sorry, I'll do it like this. So our function takes a and maps it to b. Then our inverse function takes b and maps it back to a. Now another thing to note is that I described this before, but I'm going to describe it more in depth now, that the range of the original function is the domain of the inverse function, and the domain of the original function is the range of the inverse function. Okay, so that's something that we need to be aware of. Okay, so what does a compositional function do? Okay, so a compositional function takes the value or the range of the inside function and uses it as its domain, and it pops out a value itself. Okay, so let's say that in our example here that we have f of a, right? So we know that f of a equals to b, right? So our compositional function will then take f of b, we'll take b and pop out a different value. So let's say we are using this example, for example. So it does f of a equal to b, then f of inverse takes b and it pops out a different value, right? It pops out another value, right? But looking at our example here, if f of a equals to b, then so f of inverse uses b and it leads back to a, right? So this is why the f of inverse, or the compositional function of f of inverse of f is equal to x, right? So we have a value x that leads to y, but then the inverse function is going to take that y and bring it back to x, okay? So in this case, we have, in our example, we have g of x is the inverse of f of x, and we're trying to look for f of g of 2. Okay? So we don't really need to know what g function or f function is, right? Because we can use this law to help us find our answer. Okay? So g of 2, so let's say that we have this. So g of 2 brings 2 to something of value a. All right? So we don't know what this value is, and we don't really care, because so let's say, for example, that g of 2 brings it to, let's say, a value c. Okay? So now our function f is going to take value c and link it back to 2, because c and 2 are connected. So in this case, f of g of 2 is going to equal to 2, because g of 2 brought it back to a value in a domain of function f. That function f is just going to map it back to 2. Okay? So this is how this law works, and this is the rationale behind it. Okay? So other than that, this solution is correct, and we can move on. Alright, so let's continue on with compositional functions. So let f of x equal 9x minus 2 and g of x equal negative x plus 3. Find f of g of x. Okay? So how the compositional functions work, and I'll describe it in more detail now, is let's say that this is the domain of f. Okay, or domain of g. So the g function will link it to its own range, right? So this is the range of g of x. But what happens is that the range of g of x becomes the domain of f of x. Okay? And in most cases, the entire range of g of x becomes the entire domain of f of x. And what happens is that f of x, or the function f, connects the range of g of x to a new set of values, and this becomes the range of f. Okay? So that's how a compositional function works. So this middle ground is the domain of f of x and also the range of g of x. So how we find the compositional function when they give us this? So f of x equals to 9x minus 2, and g of x is equal to negative x plus 3. Okay, so the function within the brackets is going to be the first function that we use, okay? And because of that, we're going to plug this function into our f of x function. So f of g of x can also be written as 9 times g of x minus 2. Okay, so we're going to substitute all values of x with g of x, okay? So if we were to plug it in, we get 9 times negative x plus 3 minus 2, and we get negative 9x plus 27 minus 2, and we get negative 9x plus 25. Okay? So because the range of g of x becomes the domain of f of x, then the entire g of x function is plugged into our independent variable for f of x. Okay? So if it was the other way around, for example, if we had g of f of x, then we would write negative f of x plus 3, or 9x minus 2 with a minus sign plus 3, and we would get negative 9x plus 2 plus 5, right? So these are the two compositional functions, and it matters which function is inside the brackets, okay? So other than that, the solution is correct. All right, let's move on to question number 10. All right, so this question is asking us to find the values of x that will make this equation true. All right, so they're asking us for the values of x, which will make 2x minus 3 times x plus 4 equal to negative 5. Okay, so now you can use guesswork to try to solve it, but the typical solution to this is to just simplify our equation so that we have a much more easily interpretable answer. Okay, and we can do that by isolating for x and moving all the constants to the right side. So we have 2x minus 3 times x plus 4 equal to negative 5. Okay, so we can use guesswork. We can say like, oh, if x equals 1, will that equal to negative 5? You can plug it in, right? But you can use isolation to try to find, to have the left side equal to x and have the right side equal to all the constants, right? And we're going to do that. So first of all, we're going to expand this bracket here. So 2x minus 3x plus 12, right? We're going to multiply x and 4 by negative 3, and we get negative 3x minus 12. I don't know why I put plus 12. Okay. And that equals to negative 5. So next, we see here that we have a negative 12 on our left side. We're going to move it to the right side by adding both sides by 12. And by doing that, we make this equal to 0, and we get 2x minus 3x equal to negative 5 plus 12. All right, and that would equal to, if we simplify both sides, so 2x minus 3x is negative x, and negative 5 plus 12 is 7. And by doing so, we get rid of this negative side by timesing both sides by negative 1, and we get x equals to negative 7. So now we see here that we don't need to do guesswork because we have found the value of x that will make this equation equal to 0. And you guys can check that, right? So x equals to negative 7, then 2 times negative 7 minus 3 times negative 7 plus 4 equals negative 5. Does that equal negative 5? We'll find out. Negative 14 minus 3 times negative 3, which is 9, equals negative 5. And we get negative 14 plus 9 equals negative 5 equals negative 5. So this is correct, and we know x equals to negative 7. Okay, so that's how you use isolation to find the values of x that will make this equation equal to true. Okay, this solution is correct. Good work. Finally, we're going to talk about the last question. All right, so the product of two consecutive positive integers is 11, more than their sum. So what are the integers? So integers are basically whole numbers that are positive or negative. In this case, the question specifies that there are two positive integers and they're consecutive, okay? So that means that we need to find the value of the integers. So we know that, let's say integers a times b is equal to c. Okay, we know that there is a product. So that's the first thing that we know. The second thing is that they're consecutive. So we know that b is equal to a plus 1, right? So that's the second thing that we know, that they're consecutive. And finally, we know that c, or their product, is equal to 11 more than their sum. So it's equal to 11 plus their sum. So a plus b. Okay? So if we were to combine all these together, we would get this. Okay, so first of all, we know that b is equal to a plus 1. So we can write, instead of a times b, we can write a times a plus 1. And we know that c is equal to 11 plus a plus b, and we're going to write plus a plus 1, right? Because b is equal to a plus 1. All right, so this is our, so now we can just find the integer a. And by finding the integer a, we can find the integer b. Okay, so if we were to simplify this, if we expand this left side, we will get a squared plus a. The right-hand side is going to be 12 plus 2a. Okay, so now we have to find the value of a that makes this equation true. All right, and this is going to be very difficult because we can use guesswork here, right? But there's so many variables that change our equation that it's going to be very hard. So why don't we change it? Why don't we use isolation, right? So let's move all the a's to one side and keep the constants on the other side. So a squared plus a minus 2a equals to 12. Still, this is very hard to guesswork, right? Because there are 3 a's here that can modify our left-hand side, and we're trying to find it to equal to 12, right? So let's continue to simplify here. So a squared minus a, right? Why don't we move the 12 to the left-hand side, right? So now we're trying to look for the values of a that make this equation equal to 0, right? So we didn't manipulate anything. So this is equal to this. So if we were to solve for this, we would find this, right? And if you guys can realize here, or recognize here, that this is actually just a quadratic equation, and we can factor this, we can find the values of a that equal this equation to 0. And so on and so forth, we can find the values of a that make this statement equal to true. Okay, so in this case, we're going to factor. All right, so I'm not going to go into too much on how to factor. I'm just going to do it. I'm going to use a cross multiplication method. So the factors of a are 1 and 1, and the factors of negative 12, let's use negative 4 and 3. Okay, if we were to cross multiply these together, we would get 3 minus 4, and that's equal to negative 1, and that's a coefficient of the middle term. And by doing so, we have found our factors, and that means we know that a squared minus a minus 12 is equal to 0. Is also equal to a minus 4 times a plus 3. And now we have found our factors, and now we can find the solutions to this equation easier, right? So if this bracket was equal to 0, right, so if we just need to find when a minus 4 equal to 0 and a plus 3 is equal to 0. And that is when a is equal to 4 and a is equal to negative 3. So now we have two values of a that make this equation true, and so on and so forth that make this equation true. Okay, because by our manipulation, we have equated these two to be equal to the same. However, we have known that the question restricted us to positive integers only, so we cannot use this this value here because we're only using positive integers. So therefore, a is equal to 4, and by 2, which is b equals a plus 1, b is equal to 5. Therefore, the two positive integers are 4 and 5. right? So let's just check and make sure that this makes sense to us, okay? So first of all, they have to be consecutive, and they are consecutive. So 5 is 4 plus 1. So that satisfies our first condition. A times B is equal to C, which is 20. Okay, so they have a product, sure. Most numbers have a product. But does C equal 11 plus A plus B? So does 20 equal 11 plus 4 plus 5? 4 plus 5 is 9. 9 plus 11 is 20. 20 equals 20. So we have found our answer, which is 4 and 5. Okay, therefore the solution is correct. Good work. All right. So that wraps up today's lesson. I covered 11 questions surrounding algebra and graphing and functions. So if you have any other issues with your homework or with your tests or assignments or with any mathematical concepts, please submit them to OneClass and we'll get to them as soon as possible. But other than that, I wish you guys a goodbye and I hope you guys learned something today. See you guys.